Greetings, mathletes. The saga continues. We are looking at kind of the second chunk of probability. I know it says 8-3, but it's on Venn diagrams, and I know that you've seen a little bit about them, and this might be a little bit of a review, but I want you really solid on the major concepts before we get to evil probability. So this is still approachable probability. And I know that Venn diagrams in your head look like this, right? With like two circles that have something in common and intersect. So Bruce Lee and John Wayne, Bruce Wayne, thought that was kind of cute. But Venn diagrams look like that, right? And so that's a Venn diagram initially. And I know that that kind of looks like that, and you're saying like, where's the other circle? Well, what you just saw, this is a double Venn diagram. So first let's look at a regular Venn diagram with like what's in the subset and what's not, and then we'll double Venn diagram it. So there's just a way to represent sample space, and so here's like maybe rolling a die. Here's everything that can happen on the die, we call that U. Here's everything that's A, like maybe we want a 1 and a 2. Is a you roll a 1 or a 2 and you don't have any homework for the rest of your life. So 1 and the 2 are in, and then the rest are out. This is A, this is not A. We call it A prime. And then it's easy to do probability with this because you can just say, I want the probability of A happening. You say, oh, these over the total. Now it's really often students go, oh, it's these. I've got 2 elements there, 2 things in there, and I've got 1, 2, 3, 4. And so they say half. No, right? If it's got to be a third. I want 2 out of the 1, 2, 3, 4, 5, 6. So it's got to be 2 things out of the total, which are 6, right? To give you the probability. Great. So the nitty-gritty comes into when we go into the union, and the union is both things. It's not just the intersection. It's not and. It's and or maybe you just want to say or. So it's all of this, right? That's the union, and we denote that with a big U for union. So it needs to be anything in one or the other or both. Yeah. So they would say the union is x's such that x is in A or x is in B, an element in B, this little E is an element in B, or an element in A and B. This upside down U is the intersection, and this only means and. So here's an example. Here's soccer players, tennis players. As you can see, Casey and Drew are in both. So if you put them together, Casey and Drew are both soccer and tennis players. And so if you were trying to write out the union of soccer and tennis players, you would say all of their names. Don't say Casey and Drew twice. Hey, who plays, I want an athlete, who plays soccer or tennis? You wouldn't say Alex, Hunter, Casey, Drew, Jade, right? No, you just say all of their names once, like a normal human being, because those are the people who play soccer or tennis or both. Great. The intersection is the things that have to have both. I love this. This makes me feel better about life because I didn't draw this. I just found it. So here's a beaver playing a guitar and a duck playing a keyboard, and so you get a platypus playing a keytar because it's like a mix of both. So this animal has both the tail of the beaver and webbed feet of the beaver, but it also has the duck bill of the duck, and of course the instrument is equally ridiculous. So the intersection really is just the and component. It's the things that only are together. So this is the intersection of A and B are the elements in the set of A and also have to be in the set of B, right? So you want people who play only soccer and tennis can do both, right? If you're playing a double header, you want Casey and Drew because they play both. Neat. Disjoint sets don't have anything in common. So this is my disjoint set Venn diagram. This is the set of guys that want to date me, and this is the set of guys that I want to date. It's kind of true. And it's disjoint because they don't overlap. It's a sad joke, or maybe, yeah. But we would say that they have no elements in common. There can be elements in here. Maybe evens, well, numbers below 3.5 if when you roll a die, and numbers above 3.5 when you roll a die. There's no crossover, right? We would say that the intersection is the empty set. This is not a 0 because the number 0 isn't here, right? It's not a 0. This is the empty set. It's a 0 with a seatbelt. So that says there's nothing there. It's not. You can't say 0 because I don't see the number 0 anywhere in there, and it's certainly not in the intersection. But the empty set means there's nothing there. Yeah. We would say a disjoint set is mutually exclusive. So if you know that if you picked number 1, 2, and 3, you know it's in A and it can't be in B. So everything in here can't be in here, and vice versa. Right? All right. So here's an example. Right? I like this. I set my coffee cup here and here and here twice. Here's an example. Let's try this out. Find the number of players in the club, the sporting club. This is the hockey group. This is the tennis group. This is the overall club. And so we have to interpret. So number of people in the club is, add them all up. This and this and this. And these people don't play hockey, don't play tennis, but maybe they row. They do canoe polo. So you'd add everybody up, and there's your solution. The number of hockey players is not 26 because these people also play hockey, so it's these, and so you add those groups up. So 53. Same thing. Play both sports. The number of people who play both sports is going to be just this, because these people don't play both, these people don't play both. So this is a way to say and. The people who play neither of these two sports that we're talking about, hockey or tennis, is going to be the 7 at the end, and at least one sport. So I want somebody who plays either hockey or tennis. At least means they can play double. So count them all up, right? Add them all up. Where is it? Right, it's this and this and this. These people don't count. Neat, okay. Same thing, but we're going to treat it like a probability function, yeah? So, like this piegram, like mixed together, I want some of that. We're going to take that same idea, and now we're going to stop talking about it with just regular numbers and start talking with probability. So what's the probability that you're going to pull somebody at random and that they're going to be a hockey player? Well, it's the hockey players, it's these, out of the total, which is 75, right? Great. Play both sports is 27 out of the total. Play at least one sport is the number of people that play one sport out of the total. The last one's tricky, and that's kind of the one we want to get to, is what's the probability that they play both sports given that they play hockey. This piece means that I know that this happens already. So, for example, the hockey coach sends out a Schoology message, says, hockey players, come see me at lunch. We have an important meeting. These people come in. So I walk into the room, and it's just a given that I'm talking to hockey players. Well, that means that I have 53 people in attendance. And I want the probability that, given that's happened, I want to know the probability that they play both sports. And I say, okay, hockey players, since you're here, who plays tennis? We need some help with the tennis team. And 27 of those raise their hands, right? And so that's where this piece comes from. Right, so the given limits your overall total because you, for some reason, know that you're only talking to them. All right, that's the ball game. Try some Venn diagrams. I think it looks like this. So start here with your Venn diagrams, like this. This guy has a card that has a butt and a brain and has this guy's face in the middle, and he comes over to Venn, the inventor of the Venn diagram, supposedly. He's like, hey, Venn, who do you think could have sent this to me? It's obviously Venn. Great, so start there, and I will see you later.